Hello everyone, I am Sudeep from 4th year EC. In this video, we are going to discuss two-dimensional discrete Fourier transform and its properties. To understand the topic better, we are going to discuss from what is discrete Fourier transform and why is it needed, two-dimensional DFT and its applications in image processing, periodicity, translation and rotation properties of discrete Fourier transform, and some other special cases and techniques of image processing involving the above mentioned techniques. So starting with, what does discrete Fourier transform do? To keep it simple, we can say it is used to provide frequency domain or spectral representation of a signal. The discrete Fourier transform converts a finite sequence of equally spaced samples of a function in time domain into the same length sequence of equally spaced samples of discrete time Fourier transform in frequency domain, which is a complex valued function of frequency. DFT is given by the below equation. Summation n equals to 0 to capital N minus 1, x of n multiplied by exponential of minus j into 2 pi kn by capital N. Here, capital N is the number of samples for which we are calculating the DFT. Now coming to the question, why do we need DFT? We all know the basic answer for why frequency domain analysis is required. Frequency domain graph shows how much of a signal lies within each frequency band over a range of frequencies. And also, convolution in the time domain is equivalent to pointwise multiplication in frequency domain. To get time domain signal after convolution, we can perform inverse transform on the frequency domain product. But already having discrete time Fourier transform, for that, why DFT is needed? So two features of DTFT are, it is defined for infinite length sequences and it is a function of a continuous variable omega. The above two features make DTFT impossible to compute transform on hardware. DFT also avoids above two problems and is numerically computable. That is, it is suitable for computer implementation. Now coming to our main topic, two-dimensional discrete Fourier transform. It is nothing but Fourier transform of a 2D signal defined over a discrete finite 2D grid of size m by n. Or we can also say Fourier transform of a 2D set of samples forming a bidimensional sequence. As in the case of 1D, 2D DFT, though a self-consistent transform, can be considered as a mean of calculating the transform of a 2D sample signal defined over a discrete grid. The signal is periodized along the both dimensions and the 2D DFT can be regarded as a sampled version of 2D discrete time Fourier transform. Now, why two-dimensional DFT in image processing? It is used to convert the image from the time domain to frequency domain so that frequency domain tools can be used for image enhancement. Fourier image analysis has several useful properties. For instance, convolution in the spatial domain corresponds to multiplication in the frequency domain. This is important because multiplication is a simpler mathematical operation than convolution. As with one-dimensional signals, this property enables FFT convolution and various deconvolution techniques. Most of the times, the image visible to our naked eye cannot provide sufficient information. The efficient representation of visual information lies at the foundation of many image processing tasks, including image filtering, compression, feature extraction, and many others. Now let us see direct convolution and indirect convolution through DFT in MATLAB and compare the results. Here, the matrix A is convolved with itself and the result is shown here. On the other hand, DFT of the matrix A is calculated and then it is multiplied with itself, and now the inverse DFT of the product shows the result of the convolution operation. We can observe both the results from direct and indirect operations are same. This is based on the convolution theorem, which states that convolution in the time or space domain is equivalent to multiplication in the frequency domain. Convolution may therefore be implemented using the equation mentioned here, where x and m are the arrays to be convolved. Now let us see the calculation of two-dimensional DFT and IDFT. The 2D DFT is defined as below. In the MATLAB command for the calculation of 2D DFT is FFT2 of the function. Now the inverse discrete Fourier transform is calculated as below, and the MATLAB command for its calculation is IFFT2 of the function. Here, the multiplication factor 1 by mn is used interchangeably. Now, coming to the properties of the two-dimensional discrete Fourier transform. First, the translation property. Multiplying the function f of xy by the indicated exponential term and taking the transform of the product results in a shift of the origin of the frequency plane to the point u0, v0 and vice versa for the spatial domain. This is called origin shifting. A shift in f of xy does not affect the magnitude of its Fourier transform. Coming to the second property, rotation property, this explains that if we rotate f of xy by an angle alpha, the f of uv also rotates by the same angle and vice versa. Now, coming to the periodicity property, as in the 1D case, the two-dimensional discrete Fourier transform and its inverse are infinitely periodic in the u and v direction. The 2D-DFT f of kl is periodic with periods m, n, where m by n is the size of the matrix or the image. It is proved here. Let us look at origin shifting in case of 1D signal. From translation property, multiplying f of x with given exponential term and calculating DFT results in shifting of spectrum to u0. Apply same to two-dimensional DFT. Here, origin is shifted to the point m by 2, n by 2 in two-dimensional space. The periodicities of the transform and its inverse are important issues in the implementation of DFT-based algorithms. Consider the 1D spectrum shown in the first figure. The transform data in the interval from 0 to m-1 consists of two back-to-back half periods meeting at the point m by 2. For display and filtering purposes, it is more convenient to have this interval a complete period of the transform in which the data are contiguous as shown in the second figure. That is, multiplying by f of x with minus 1 power x shifts the data so that the origin of the spectrum is at the center of the interval 0, m-1, which corresponds to the second figure as desired. In 2D, the situation is more difficult to graph, but the principle is the same. As third figure shows, instead of two half periods, there are now four quarter periods meeting at the point m by 2, n by 2. The dashed rectangles corresponding to the infinite number of periods of the two-dimensional DFT. As in 1D case, visualization is simplified if we shift the data so that the point is at m by 2, n by 2. We can do that by choosing u0 and v0 as m by 2, n by 2. This shifts the data so that origin is at the center of the frequency rectangle defined by the intervals as desired. We can see that in the figure. Now we will see how the properties we have learned so far are useful in image processing and how are they valid. In this, image 1 is a simple image under consideration. Image 2 is its non-centered spectrum showing bright spots in four corners, which we cannot see clearly as the origin is not yet shifted. The image shows its spectrum whose values were scaled to the range 0 to 255 and displayed in the image form. The origins of both the spatial and frequency domains are at the top left. To center the spectrum, we simply multiply the image in A by computing the DFT. Image 3 is the centered spectrum, that is, after shifting the origin, showing a bright spot at center. But still, we cannot get much information from it because the DC term dominates the values of the spectrum. Image 4 is showing increased detail after log transformation. So, what is DC term and why the log transformation is required here? As we can see, 2D-DFT is calculated using the formula shown. If we find the value of the spectrum at origin, it is equals to the Mn multiplied by the average value of the original image. Because the proportionality constant Mn is usually large, magnitude of spectrum at origin typically is the largest component of the spectrum by a factor that can be several orders of magnitude larger than the other terms. Because frequency components u and v are zero at the origin, the spectrum at origin sometimes is called the DC component of the transform. So, the dynamic range of other intensities in the displayed image are compressed. To bring out those details, we perform a log transformation defined as 1 plus log modulus of f of u, v. Now let us try to perform operations like origin shifting and log transformation on a given image in MATLAB and observe the results. Image on the left is our input image. Remember this image as this will be our reference image further. We can see the magnitude and phase spectrum without origin shifting. We can't observe any details in the magnitude spectrum. Now shift the origin and observe the spectrum. A bright spot in the middle can be observed, but phase spectrum is unchanged. Now perform log transformation and we can see detailed magnitude spectrum. Now let us perform some operations on the translated and rotated versions of our reference image and compare the spectrums in the end. Let's see the results for the translated image. In the left, we can see translated reference image and in the right, magnitude and phase spectrum with no much detailing. We can observe change in phase spectrum from original reference image. After origin shifting, a bright spot in the center of magnitude spectrum is observed. It is same as that of original reference image, even though input image is translated. Here we can observe magnitude spectrum after log transformation. Let's see the results for rotated image. In the left, a 45 degrees rotated image and in the right, magnitude and phase spectrum without origin shifting can be observed. After origin shifting, you can observe that magnitude spectrum is also rotated by 45 degrees as compared to that of magnitude spectrum of the reference image. Phase spectrum is also different. Image spectrum after log transformation is also rotated by the 45 degrees. Let us try to understand the results by comparing them. Compare the original result with the rotated image results. If the image is rotated by certain angle, the magnitude spectrum is also rotated by the same degree. It can be observed from the given images. If we compare the translated image result with the original results, magnitude spectrum is unchanged, but phase spectrum is changed. Now let us try to get the overall overview. If the image is translated, magnitude spectrum remains unchanged, but phase spectrum changes. The image is rotated. Magnitude spectrum is also rotated by the exact angle and the phase spectrum is also varied. Thank you.